All right, let's dive into one of C++'s most famous and sometimes confusing inheritance puzzles. Yep, we're talking about the diamond problem. But we're not going to use a bunch of abstract theory. Instead, we're going to solve a little mystery inside a hospital system. So, let's kick things off with a question. It seems simple on the surface, but in the world of code, it gets complicated fast. In a hospital, is it possible for a doctor to also be a patient? Of course. A resident doctor who's there for their annual checkup is a perfect example. And that exact scenario, it's the key to unlocking this whole C++ puzzle. Okay, so to build out our system, we need a foundation, a fundamental building block. And for us, that's going to be a base class called person. Just think of it as the common ancestor for everyone. Whether you're the head of surgery or the newest patient, you are first and foremost a person with a name and an age. Now, from this general person class, we can start to specialize. We'll create two more specific types, a patient class and a doctor class. Now, both of these inherit the basic stuff from person, that name and age, but they'll eventually have their own unique properties too. And here is where our puzzle really starts to take shape. To model that person who's both a doctor and a patient, we need a resident doctor class. This new class is going to inherit from both the patient class and the doctor class. And when you draw that out, you can literally see the diamond forming. You've got person at the very top, patient and doctor in the middle, and then our resident doctor right at the bottom. And this structure, this is the textbook definition of what we call the diamond problem. It happens anytime a class, in our case, the resident doctor, inherits from two other classes that themselves share the same common ancestor. This creates two paths back to the person class, and that gives the compiler a massive headache. So why is this such a big deal? Well, because our resident doctor inherits from patient. It gets a complete copy of all the person data, a name and an age. But wait, it also inherits from doctor, which brings along its own copy of the person data. So now our poor resident doctor object literally has two sets of names and two sets of ages. One came down the patient path, and the other one came down the doctor path. This leads to a very practical crisis. If you try to ask the resident doctor object for its name, which name are you talking about? The one it got from being a patient or the one from being a doctor? The compiler just throws its hands up in the air. It's totally ambiguous and it has absolutely no way to know which one you want. But don't worry, the amazing people who designed C++ saw this coming, and they gave us a really elegant and powerful way out of this jam. And it all boils down to one single super important keyword, virtual. So how do we actually use it? On the left here, you see the problem code that creates those two copies. On the right, you see the fix. And the key here is that we're not changing the resident doctor class at all. The magic happens in the intermediate classes, patient and doctor. We just add that virtual keyword right when they inherit from person. So what is this virtual keyword really doing under the hood? Well, it turns person into what's called a virtual base class. This is basically a special instruction to the C++ compiler that says, hey, listen, I know you see multiple paths leading back to the person class, but I want you to make sure there is only one single shared instance of person in the final object. And just like that, the two paths merge and the ambiguity completely vanishes. Okay, so understanding the theory is one thing, but seeing it work in the actual code is where it all really clicks into place. So let's walk through the full corrected C++ code from our source and see just how clean this solution is. Here are our class declarations. You've got person up at the top, our foundation. Then look closely at patient and doctor. You can see it right there, virtual public person. That's the secret sauce. And then finally, resident doctor just inherits normally from both of them, and everything gets pulled together perfectly. And check out how beautifully simple our main program becomes now. We just create our resident doctor object, we call a single input function, and now the compiler knows exactly which input person method to use because there's only one. And the same thing for display. It finds the one and only display person function and shows our unified data. It's clean, it's simple, and it just works. This quote really nails it. The whole problem comes from having multiple, separate instances of the base class. The genius of virtual base classes is that they don't just pick one path over the other. They provide a way for those paths to converge and share a single foundation. So let's quickly recap this whole mystery. The diamond problem is just that ambiguity you get when two inheritance paths lead back to the same grandparent class. The solution? That incredibly powerful virtual keyword. And you don't apply it at the bottom of the diamond, you apply it in the middle.
This creates one shared instance of the base class, the ambiguity is totally gone, and our code runs exactly like we want it to.
And that is how you elegantly solve the diamond problem in C++. It's a fantastic example of how even really complex, real-world relationships can be modeled perfectly if you just have the right tools. Which kind of leaves you with one final question, right? Now that you know how to solve this puzzle, what other inheritance mysteries might be hiding in your own code?